Good afternoon, everybody. This is Lorenzo Perella for Physics 116 with Clark Wellman. Today, this video will cover Quiz 4, question number 2, involving sound waves. As you can see from this photo, the data has a frequency measurement of air that's blown across the top of a pipe that has an inner diameter of 3 centimeters, and that the air temperature during the measurement was 27 degrees Celsius. If the measured length of the pipe is L, the corrected length LC used to calculate the resonance frequency of the pipe is LC plus the length plus 0.33 times the diameter times the number of open ends. And we see that the peak frequency is at the first overtone. So we use this frequency to start with these questions. Now the first part is what is the sound speed in air? And then we have to see whether or not this is an open pipe or open closed pipe. In order to get the air speed, what we do is that the velocity of the wind is a constant of 331 meters per second multiplied by the square root of the temperature of air in Kelvin divided by room temperature Kelvin. Now to get the temperature of Kelvin that we're looking for, we take 27 degrees Celsius and add that to 273.15. Our end result is 300.15 Kelvin. And then the room temperature Kelvin is 273.15 K. We do this together and we find that the velocity is 347 meters per second. Whereas this part B, we can see from the graph generated that this pipe seems to be an open one. For that, how the second harmonic has the largest amplitude, and we can see that mirrored in information from our chapter 17 notes. And as you can see, when it comes to the first overtone, the wavelength has all of its illustrations done so, which is the illustrating of the length, whereas the fundamental, it's 1/2 of the wavelength, which when you go back to the provided photo shows that the first overtone is twice that of the fundamental. All this compiled together gives suitable reason to see this kind of information showing that this pipe is open. Third, what is the fundamental frequency of the pipe and what is the first overtone of this pipe? To get these illustrations, what we do is first take the average frequency of the first overtone, which is 1003.42 Hertz plus 1005.86 Hertz. You divide this by 2, you get 1004.63 Hertz. Then half of that will give you the fundamental frequency, 502 Hertz. And then the first overtone is just the first half of it's just twice that of answer C. And finally, second to finally, we have to figure out the length of the pipe. Now before, we saw that the corrected length is the length plus 2 times 0.33 in the diameter. And we also take into account that the second frequency is the velocity divided by the length corrected. Now in order to get this length corrected, we have to take 1004.67 Hertz, divide that equals 347 meters per second in length. So in order to get the length corrected, we get 347 divided by 1004.64 seconds inverse, which is the same as Hertz, and you get 0.345 Hertz. Meters. 0.345 meters. And then when you apply that to the LC, what you have is 0.345 is equal to L plus 2 times 0.33 times 3.0 e minus 2 meters, which is 0.345 meters minus 0.0198 meters, which makes the true length to be 0.326 meters. Finally, without changing the pipe length, how can you change the fundamental frequency by a factor of 2 or 1/2? This can be done by simply closing one end of the pipe. By doing so, we make the air circulate, and by doing so, it increases and lowers the amount of the frequency that is generated. In order to get this, what we do is apply the first frequency for a closed open pipe, open closed I mean, and we find that one frequency for this is of half is 244.44 hertz. And then for the first overtone, which is roughly 3 times of that, it allows you to get 732 hertz. And this can be seen like with a clarinet or oboe. It's a very real-world problem that you can solve for. Thank you for tuning in today. This has been Lorenzo Perella for Physics 116 Clark Wellman. Have a wonderful afternoon.